We are living in the world of uncertainties. And so, in most of the cases, we are bound to take decisions under uncertainties. Needless to say that a correct decision would lead us to some advantageous and favorable state, whereas a wrong decision may lead us to some disadvantageous and unfavorable state. In the situations where we have to take decisions under uncertainties, we usually take help of probability. But how many of us have correct, flawless, and clear understanding of probability? Probability may seem difficult to calculate, but it is more difficult to interpret. Common people generally have misconception of probability, and they fail to take a correct decision on the basis of probability. Today, I would like to make you acquainted with some common mistakes that common people do while dealing with probability. It is not possible for anyone to describe all such biases that people suffer from while interpreting probabilities. However, I would like to elucidate a few of them with some examples. First example. Suppose you have been given a choice to select either of the two games. In the first game, you can win 1 crore rupees, and in the second, 10,000 rupees. The probability of winning in the first game, that is winning 1 crore rupees, this probability is 1 in 10 crore. And in the second game, it is 1 in 10,000. Now the question is, which one do you choose? The first game or the second game? Often the people's emotions draw them to the first game, even though the second is 10 times better if considered objectively. People are always attracted to the larger amount, no matter how small the probability is. Second example. It is the common nature of people to invest in startups because the potential profit makes amount sign flash before their eyes. But they do not investigate the little chances of new businesses actually achieving such growth. Similarly, following extensive media coverage of plane crash, people start canceling flights without really considering the probability of crashing, which remains the same before and after such a disaster. Neglect of probability leads to errors in decision making. Now, let me give the third example. Suppose there are two methods of treating drinking water. Let a river have two equally large tributaries. One tributary is treated using method A, and this reduces the risk of dying from contaminated water from 4% to 1%. The other tributary is treated with method B, which reduces the risk from 1% to 0%. So which one is better? Method A or method B? Most of the people would say method B because it is from 1% to 0%. But how silly is this? With method A, 3% fewer people die, whereas with method B, just 1% fewer people die. And so, method A is 3 times better than the method B. Fourth example. Suppose that a test for some disease, say cancer, presents a rate of 5% false positive. That is, out of 100 persons, 5 persons are wrongly found suffering from cancer, although they do not have cancer. Now, suppose that the prevalence of this disease in the population is 1 in 1,000. People are tested at random, regardless of whether they are suspected of having cancer or not. A patient's test is found positive. What is the probability that the person actually suffers from cancer? In such cases, it is generally believed that it is 95% likely that the person has cancer. Even most of the doctors say that it is 95%, simply taking into account the fact that the test has 95% accuracy rate. But the fact is entirely different. It is the case of conditional probability and can be solved using the Bayes theorem. Let us solve it. Let E1 represent the event that the person suffers from cancer, and E2 represent the event that the person is cancer free. He doesn't suffer from cancer. Let event A represent that the test is found positive. Now here E1 and E2 are two mutually exclusive and exhaustive events. E1 is person suffering from cancer, E2 person not suffering from cancer, and A is the event that represents that the test is found positive. Now what we have been given here? We have been given the probability of E1 equal to 1 by 1000, that is 0.001. That is probability of a person suffering from cancer is 0.001. Obviously, probability of E2, that probability of a person not suffering from cancer, would be 1 minus 0.001, that is 0.999. Now the conditional probability of A given E1, that is probability that the test is found positive when it is given that the person is suffering from cancer. Obviously, it would be 100%. Probability of A given E2, that the probability that the test is found positive when it is known that the person doesn't suffer from cancer. This is 0.05. That is given. Now the well-known Bayes formula is, we have to find here probability of E1 given A, that is the probability that a person suffers from cancer when it is found the test positive. Now this is probability E1 into probability A given E1 whole divided by probability E1 into probability A given E1 plus probability E2 into probability A given E2. When we would substitute the respective probabilities in this expression, the final result comes out to be 0.01963. It is less than even 2%. Where you were saying that it is 95%. But the actual probability is less than 2%. How surprising is this? Let me simplify the answer using the frequency approach. Out of 1,000 persons, one is expected to suffer from cancer. Out of the remaining 999 healthy persons, 999 into 0.05, that is 49.95, would be identified with cancer. Thus, the probability of a person suffering from cancer is the following ratio. Number suffering from cancer divided by number of true and false positives, which is equal to 1 by 1 plus 49.95. That is 1 by 50.95, which comes to be 0.01963. The same probability obtained from the Bayes formula. Now let us take the fifth example. Suppose in a family there are two children. It is known that one child is a boy. The question is, what is the probability that the other one is also a boy? That is, out of two children, one is a boy. Now we have to find the probability that other child is also a boy. An obvious, quick, and most expected answer to this question is 1 by 2. Half. 50%. But if we solve it using the probability rule, the answer would be different. Here, there would be total 3 possible cases only. Boy, boy. First child is a boy, the second child is a boy. Boy, girl. The first one is boy, the second one is a girl. And the third case, girl, boy. First child is a girl, the second child is a boy. So there are only 3 possible cases, because the case of both children being girls is ruled out. Thus, the required probability, that is the probability that the other child is also a boy, is 1 by 3. It is not 1 by 2. Sixth example. People at large generally have biased understanding of life expectancy. Just a few days ago, an agent of a financial investment company was suggesting me that as the life expectancy of an Indian is 70 years, and I have already completed 65 years, I can expect to live 5 more years. And so I should plan accordingly. He went into various investment plans to prescribe for me that I should invest for a 5 more years horizon. I asked him that had I been of 75 years, then was my life expectancy minus 5 years? He looked perplexed at my this question. About what that agent was confused was the conditional and unconditional life expectancy. At birth, our unconditional life expectancy may be 70 years. But as we advance in age and do not die, our life expectancy increases along with our life. Why it is so? Because other people, by dying, have taken our spot in statistics, since expectation means average. So if we are 70 and are in good health, we may still have, say, 10 years in expectation. But the expectation would change, and at 80, we will have another 5 years, provided, of course, we are alive. Even someone 100 years old still has a positive conditional life expectation. Seventh example. This is a very famous example in probability, where people generally get confused over its result. This is commonly known as birthday paradox. Though, in my opinion, it is not really a paradox. It is simply a perceptional oddity. If you meet someone randomly, the probability of sharing his birthday with you is 1 in 365.25. That is 1 by 365.25, which is equal to 0.00274. I mean to say that the probability that two persons have the same birthday, date and month only, not the year. So the probability that the persons have the same birthday is 0.00274. It is very small. A very, very rare event. Now, let us look at the situation where there are 23 people gathered somewhere. What is the chance of there being two people with the same birthday? You will be surprised to know. It is 50%, about 50%. It is like this. In a group of 23 persons, probability that no two persons have the same birthday is equal to 365 by 365, because the first person may have any birthday out of the 365 days. The second person, the probability would be 364 by 365. For the third, 363 by 365. And in this way, for the 23rd person, this probability would be 343 by 365. So the probability that no two persons have the same birthday is 0.4927. 0.4927 is the probability that no two persons out of 23 persons have the same birthday. Thus, probability that two persons have the same birthday is obviously 1 minus 0.4927, which is 0.5073. 50%, more than 50%. Is it not amazing? Why in case of only 23 persons, the probability of two of them to have the same birthday comes out to be more than 50%? Common people fail to understand it. In fact, in this case, we are not considering any specific pair of persons. We consider all the 23 C2 pairs, that is 23 into 22 by 2, which is equal to 242 pairs of the persons. Any one or more of these 242 pairs may have the same birthday. This is why in case of only 23 persons, this probability goes beyond 50%. A similar misconception of probabilities arises when we suddenly meet some relatives or friends at some highly unexpected places. We, in that case, utter in great surprise, "Oh, the earth is round. The world is too small." But the world is larger than we think. It is just that we are not considering the probability of meeting some specific person at a specific place at a specific time. Rather, in such situations, we simply mean the probability of meeting any person we have ever met in the past and at any place we visit during the period concerned. The probability of meeting any person we have ever met in the past and at any place is considerably higher, perhaps several thousand times the probability of meeting some specific person at a specific place. There are many other biases in understanding probabilities, many other misconceptions about probability. Let us hope we would discuss those sometime in future. Thank you.